Okay, let's start for today. Right. So today, right, before we have already completed chem bonding last lesson, right? Okay, so this week, rightfully I should be starting a new chapter, but I don't want to go too fast yet. Okay, next week then we start the next chapter called gaseous state. Okay, for this week, we're gonna do like a little worksheet with questions, okay, for whatever we've learned so far. Okay, and I think the most appropriate one will be chem bonding, right? Okay, so here you go, here one worksheet. And we're going to try some easy questions, some rather challenging questions also. Okay, because RI has a lot of application questions, right? Chem bonding, they can come out of a lot of different things. Okay, so today our goal is to do as many questions from here as possible. Okay, we're going to start off easy first. Okay, then later we're going to get a little bit more difficult. All right. So I need you guys to take a look at question one, or let me just roughly just recap with you guys the main ideas in chem bonding. Alright, so if it's been a while for some of you guys, okay, so let me just show you all what is required first. Okay, so quick summary, right? Okay, chem bonding, we are looking into the main idea, which is physical properties. We are studying chem bonding to explain physical properties such as melting points, boiling points, and solubility. There are certain questions here that we're going to explain some different types of physical properties as well. Okay, apart from melting points, apart from solubility, you will start to see some new ideas as well. Okay, but it's everything that we have within our scope that we have learned before, right? Okay, so not to worry. Okay, so today we're going to do a few things. Usually the main core concepts, right? VSEPR theory, structure and bonding, and intermolecular forces. Okay, if you were to look at chem bonding from a larger scale perspective, right, it will be these three main ideas. So we're going to see different types of applications later on. Okay, whenever you encounter a question, right, it is important for you guys to identify what question type it is first before you can dive into the question itself. Okay, sometimes it's easy to identify, sometimes it's a bit more difficult. Okay, so we're going to take a look at this worksheet. We're going to start off simple first. Okay, can you look at question one? All right, so how we're going to do time questions in class, right, is that I'm going to time you guys, okay, based on the amount of marks that they've given you guys here. I might give you guys a bit more time because I want to see some quality answers. All right, okay, so we start off with question one, a rather simple two-part question. Total is 3 marks, right? Okay, let me just introduce to you guys first. 1 mark is usually 1.5 minutes. Now, this is the exam condition. So they will allocate time based on the number of marks and then they just multiply by 1.5 minutes. Okay, but for now, because you guys are just starting out, I don't want to rush you guys yet because you're not really there yet. Okay, in terms of knowing how to do the questions. Okay, it takes time for you all to spot. So I'm going to give you guys more time for this 3-mark question. Okay, perhaps right, starting more time than necessary, I'm going to give you guys 5 minutes. Okay, so we see whether we can finish question 1 within 5 minutes. 2 parts. All right, these 2 parts are things that we've done before, not much application involved yet. Okay, so just give it a try. Okay. Oh yeah, one more thing to mention first. Okay, so if you look at part 2, right? Some of you guys don't know what cyclohexane is yet. So I'm just going to tell you all the molecular formula, C6H12. That's the molecular formula alone, right, is enough to do the question already. Okay, so here we go. Right, give this a short. Yeah, time you guys. So about 4 minutes left. if you need to, you can refer to the answering technique, the answering format of solubility questions. Okay, but again, you still need to apply it to this context. We have 2 minutes left. If we have 1 minute left. Yeah, I'll give you 1 final minute to tidy up your answers. Okay. And time's up. All right. Okay. Okay, nice. Okay, so that was your first kind of time trial kind of situation, right? Okay, so you can identify the 2 questions. I'm pretty sure you guys know what concept it is very easily. You notice at the top of the question, right? Okay, I actually identify these question types for you guys. But as time goes on, you need to know how to identify these questions yourself. First one is not across, second is clearly solubility. Okay, so guys, take a look first, I3 minus. I3 minus is a rather interesting compound, right? Because it's both an ion, that's the special part, and at the same time, there is a negative charge. Now, guys, do you all remember what a negative charge means? We have to add an electron to the what? Okay, the more electronegative atom, can you remember? Okay, in this case, it doesn't matter because all of them are iodine. But then the issue is, do you add the extra electron to the side atoms or to the central atom? Okay, there's no hard rule saying where you need to add it. Okay, but that's why here you can trial and error. Okay, so let me show you guys the wrong version, which is to add it to the center. Okay, guys, iodine currently all of them have how many valence? 7 each. Okay, if you try to add the electron to the middle guy, is going to end up with 8 valence electrons, right? Guys, if you have 8 valence electrons, what kind of bonds can you form with the side? Okay, what kind of bonds can you form? Okay, so you think of dative bonds, right? Okay, but we do, okay, then we try dative bonds first. Okay, so in this case, iodine in the center gives 2 dative bonds to the side, right? Okay, but then the rest of the iodines have 7 electrons. Okay, can we fill in 7 electrons here? 1, 2, 3, 4, 5, 6, 7. There's going to be 1 lone electron, right? Okay, and that's not possible because iodine in total over here has how many valence? 7 times 3. By D plus 1, right? Okay, because we got the extra electrons. So this is an even number. So you're not allowed to have an even number of electrons here. Okay, so we know that adding to the center is just not viable. Okay, instead what we can do here is to add it to the sides. Okay, so next time, right, another compound that you all can take note of is N3 minus. This is known as an A side ion. And it's the exact same principle as the I3 minus ion. Okay, do note, right, for these kind of compounds, you add the extra electron to the side. Because guys, if this guy has 8 valence electrons, so 7, 7, 8, what kind of bond can this guy form? 8 electrons is dative bond, right? So dative bond, let's just give it to the center. So you can see it's all dots. Make sense? Okay, then we try to fill in the rest. 7 electrons can fill how many bonds? 1 bond, right? So for 1 bond, okay, let's just do this. If this is dot, this is cross, then this one must be dot also. Okay, so 1 bond just looks something like this. Are we able to fill up the rest of the valence electrons on the center iodine? Yes, right? Okay, the center iodine is 7. We already used 1. So how many lone pairs is this? 6. 1, 2, 3 lone pairs. Make sense? Okay, so they also mentioned, right, that this is a linear structure. And I hope you all can tell me how many bond pairs and how many lone pairs are there on the central atom? How many bond pairs are there? 3 bond pairs? Sure. There's only 2 bond pairs, right? Okay, 2 bond pairs and how many lone pairs? 3. So 2 bond pairs, 3 lone pairs will actually give you your linear shape. Okay, so this one you kind of need to know your BSEPR as well. So that's how we know, right, that this structure is definitely correct. Okay, they gave you a clue as well. Okay, so if I want you guys to draw the full structure as well. Okay, as you can see here, I have a single bond and then I have a dative bond. Now I want you all to notice, right, the dative bond is giving from the side to the center. Now I did clarify this with you guys before. Usually dative bond is from where to where? Okay, we've already emphasized this point. It's usually from the center to the side, right? Okay, but that one is only if the central atom cannot hold more than 8 valence. I repeat, if the central atom cannot hold more than 8 valence, then your dative bond is from the center to the side. But in this case, it's not about the situation. Here you are just given 1 extra electron. 8 valence, no choice. The dative bond must be from the side to the center in this case. So it's a rather interesting version of a dot and cross diagram. We haven't really gone through this kind of scenarios before. So take note, right? Another scenario they can ask, right, is N3 minus. This one, in fact, is in our tutorial, Chem bonding. Okay, so you can give N3 minus a try on your own time as well. Okay, but convert it to the structure because they may very well ask you to convert it to the structure. Okay, future questions, they may not be as nice to tell you that it's a linear shape. Then you need to figure out for yourself. All okay with this? Yeah, okay, so rather advanced dot and cross diagram. Okay, then now we look at part 2. Part 2, the answering technique, right? There's not much for me to discuss. Okay, it's energy release versus energy required to overcome. Same thing, guys, just highlight the word insoluble or immiscible. Okay, they tell you whether it's soluble or insoluble, and your job is to work towards the explanation. So, guys, remember this diagram here. Okay, can you identify all these interactions with me? Water, what's the interaction? Okay, hydrogen bonds. Okay, this is quite simple. Okay, but you take a look at cyclohexane. Now, because you all haven't learned organic yet, I don't expect you guys to know what cyclohexane is, so I give you C6H12. Based on this information alone, can you all tell me C6H12 is what interaction? ID. How do you know that? Because C6H12 is a what kind of molecule? Non-polar. Okay, we know it's non-polar because it's literally only made up of carbons and hydrogens. We mentioned before, okay, carbons and hydrogens non-polar. So that's how we know it's non-polar. Okay, later, take note of this, let me repeat. Carbon and hydrogen alone is non-polar. Later, there's another question which I need you all to recognize this. Okay, so guys, you see a non-polar and a polar molecule, usually do they mix with each other? No. Okay, I mentioned different kinds of molecules don't mix well. So in this case, what's the blue color interactions called? Okay, yes, IDID, which is some very weak IDID attractions because they're not compatible, so they don't really like each other. Does that make sense? Okay, so that's how we know. That's the answer. Do you think the IDID formed between the two molecules is enough to overcome hydrogen bonds? Definitely not, right? Maybe it can overcome IDID, but definitely not hydrogen bonds. That's why it is insoluble. As for the answering format, right? Okay, so you can tell me energy released from the weak IDID attractions. You can include the word weak to really showcase that it's not enough. The word not enough means insufficient to compensate for the energy required to overcome the ID-ID attractions in cyclohexane and hydrogen bonds in water. Okay, honestly, I'm not too worried about the answering format because you guys just need to get used to it yourself. What I'm more concerned with is whether you can identify the correct types of interactions. Okay, and generally, the type of molecule can bring you towards the correct interaction. All okay so far? So it's a rather simple question. Honestly, this one is nothing special, honestly. Okay, we're just going to move on to different types of questions now. Okay, so far, any questions for question one? No? Okay, good. Okay, we're going to try a rather simple question. Okay, question two. It's just an application question, but I think it's an easy application. So I'm going to give you guys some time to try this. Okay, let me see how many marks. Okay, so in total, we have 4 marks. Okay, yeah, this is honestly quite simple. I'm not going to give you guys, I'm going to multiply by 1.5, right? That's 6 minutes, which I think is too long. Okay, so I'm going to give you guys 4.5 minutes. Okay, 4 to 4.5. Because honestly, right, pretty easy question. Okay, so let's move on. Question 2, do the whole thing. 4 to 4.5 minutes. Right, I'm going to extend the time. So we can afford to extend the time because I undercut the time intentionally. So we try 5.5 minutes. We have about 1 minute left. If we have hit the 6 minute mark, I'm going to give you guys 2 extra minutes to finish this up. Okay. Down to our final minute. Thirty seconds left. Okay, and time's up. All right. So let's talk about time for a bit first. Okay, so you guys took 8 minutes for this question, which is okay, because this is basically how you can allocate time for yourself. This is the optimal time allocation. 1 mark is 1.5 minutes, so you should aim to do this in 6 minutes eventually. Okay, because we just started, right? Okay, so that's why we can afford to go to the upper range, the upper bound, which is 1 mark 2 minutes. That's still reasonable. Okay, but try not to go anything beyond 1 mark 2 minutes, which is beyond 8 minutes. Okay, so you should have like contingencies. So this is the contingency. This is the fast case scenario. Okay, because as you get better and better, right, at time management, sometimes you don't actually need the whole 1.5 minutes to answer a 1 mark question. Sometimes 1 mark questions can be very easy and very fast to get, but sometimes like you look at the first part of this question, it's slightly more difficult to get this 1 mark. And that's what I noticed. Okay, some of you guys spend a little bit too long on your first part because it's only 1 mark, right? Okay, from an exam perspective, you shouldn't be writing too much for this and you should be moving on very quickly. Okay, so we're building time management skills from the get-go, okay, not towards exam, okay, from now. Right? So the idea is when we look at time management, right? Okay, number one, don't write too much for the first question. Number two, even if you're not very sure of the answer, please move on to the rest. Because you never know, sometimes the marks later on are a lot easier to obtain than let's say this question here. Okay, guys, how do we explain this question? Okay, notice the three main ideas are. This is clearly on PSEPR theory, right? Because we are explaining the different bond angles. Okay, for this, right? Okay, you kind of need to draw the structures first. Okay, but I think, right, it is necessary for you to know how carbon dioxide should look like from now on. Certain structures, for example, CH4, water, ammonia, and carbon dioxide. These are essential molecules. So you should know the shapes of these guys, right? It's like from memory, so no need to draw. Like you should know how it looks like from it. Okay, linear, bent, tetrahedral, trigonal, pyramidal. So it's like the 4 basic shapes. Yeah, I never write trigonal planar here, okay, but not much trigonal planar, okay, when we look at basic structures. Okay, by the way, carbon dioxide here is 180. Sulfur dioxide, you might need to draw out yourself. Okay, so we will arrive at this shape here. And you notice why this 1 mark is not very worth it, right? It's not very worth your time because you need time to draw SO2. Okay, and then you need time to answer the question. So this 1 mark is one of those cases where you need to try to move on if you run out of time. So guys, let's take a look okay, at the appropriate explanation. Does anyone need me to draw SO2 for you? Okay, this one we went through it dot and cross, I think twice already. Okay, so take a look here. Why is it that the bond angle of carbon dioxide is larger? How do we explain questions like this? What must we talk about? What must we compare? Bond angles are different because of different repulsions. Good. Okay, so what's the repulsion in the carbon dioxide? The repulsion is a bond pair repulsion, right? According to PSEPR. Whereas for this one, the repulsion is lone pair, bond pair. Can I ask you which one is stronger? Definitely the one on the right, right? Because the repulsions are stronger, it's going to cause them to be, you're going to force the bond angle to be smaller. So all you need to tell me in the question is this, just 1 mark. Okay, the lone pair, bond pair repulsions in SO2 is stronger than the bond pair repulsions in carbon dioxide. So what I want you guys to avoid is this. SO2 has lone pair repulsions. Full stop. Carbon dioxide has bond pair repulsions. Full stop. Then you tell me lone pair repulsions are stronger. You see how slow this is. Okay, get to the point. Okay, just immediately tell me what they have and just compare immediately. Because for 1 mark, you don't have time to write 2 marks. Okay, so this is how you cut your answer down. It's stronger, and you can just tell me hence the bond angle of SO2 is smaller. Finish. You want to say smaller than bond angle of carbon dioxide also can. But honestly, that part doesn't give you marks anyway. The 1 mark, right, is to compare strength. That's why the rest of your answer you can just cut it down. Honestly, not bad. Okay, that's 1 mark. Okay, as you can see, it's not very worth it. It's not very worth the time. Okay, and these are questions that you encounter in exam. And then I don't want you guys to spend too much time on just this one time. So we're going to create this thing called red flag intuition. If the question is not worth it, right, it's a red flag, and then you should move on. Okay, Ken? So guys, let's move on to the Van Acker triangle. Now you're going to slowly see more things like this. This is a very easy application. Okay, Van Acker just tells you about the type of bonding in the 3 points of this triangle. Okay, I'm pretty sure you'll read the whole thing already, right? I hope you all can understand why the numbers are like this. Anyone need me to explain? Okay, so for carbon dioxide, okay, this is just math, I'll just calculate. It's 3.05 and 1.1. Then when you mark your diagram that time, right, it should be somewhere here-ish. Okay, that one just go and mark on the graph. And don't just put a cross, I think it's safer to put that carbon dioxide as well. Okay, so we leave carbon dioxide there, and then later, right, we take a look at what this is leaning towards. Okay, can Alright, okay, let me look at A and B. Can someone tell me what is the type of bonding in A? Okay, they tell you guys that C is ionic bonds, ionic bonding. So what's B and A? Okay, what's A first? Okay, A is actually metallic. Okay, so B is actually covalent. Okay, let's explain this. Okay, this one might be a bit confused with the graph. Okay, so let's explain the graph first before I look at the answer. All right, you must look at the data and relate the data back to your own knowledge. What does point A represent? It is on the x-axis, right? So it has 0, 1. 0 this or 0 this. It has 0 difference in electronegativity. So you think about it first. When you have no difference in electronegativity, it implies both atoms are the same or similar, right? Okay, so you could think of covalent bonds, and that's probably why most of you guys immediately flock to covalent bonding. But then you have to understand P also has no difference in electronegativity. So it could also be covalent bonding, we don't know. But the only difference between A and P is the x-axis. P has much more, much higher average electronegativity. What does that imply? Okay, so remember, covalent bonds occur between what kind of compounds? With what kind of elements, sorry? Covalent bonds usually are non-metals, right? Metallic is quite obviously metals. Okay, and we know metals are on which side of the periodic table? The left. And the left, right, your electronegativity is low. So you need to know your trends, okay? Left side of the table, electronegativity is low, but non-metals on the right-hand side, so you must have higher average electronegativity. In other words, this corresponds to the points. B has a higher average electronegativity, so definitely covalent compounds, covalent bonding, or covalent bonds. A, much lower electronegativity, just think of metals. Okay, so okay. This number here represents the average electronegativity. The reason why they gave you this, right, is to look at this is an example for how it looks like. Then you try to arrive at these values. Okay, so this is the difference in electronegativity, and it corresponds to carbon and oxygen. Okay, where is it? Carbon and oxygen, you add together and you divide by 2. Okay, so this one is also silicon plus oxygen, you divide by 2. You should test your answer out. Okay, because some of you guys might times 2 to the oxygen because you don't know whether you don't know how this shit works, right? Okay, so you will probably times 2 to the oxygen. You don't know, right? Okay, so you need to test. That's why you give an example like this to test your answer. Okay, so 1.1 is just minus of, okay, carbon minus oxygen. Or opposite, yeah. Okay, can? Okay, good. Okay, so last question, very simple. Or now maybe you can use this Van triangle for a more appropriate purpose. Now you can see the 3 points on the triangle and you will understand what this triangle is actually used for. Okay, your carbon dioxide is leaning towards the covalent side, right? You all see, based on your point. Okay, imagine that you calculate this wrong, then your carbon dioxide end up here, definitely wrong already. If your carbon dioxide here also wrong, okay, must be closer to P, something like this. Okay, can? What's the final answer here? Al2O3 is what then? Al2S3? There are 3 options, right? Okay, which one? Okay, good, more ionic. Okay, how do we know that? Is higher. No, that's the wrong explanation. Okay, both of them are +3 minus 2, +3 minus 2. So nothing to do with charge. What has it got to do with? Exactly. After we do all this, right, then you notice it's all about electronegativity. We know the more ionic you are as compound, maybe I'll take this out. The more ionic you are, that means what? An ionic compound has a larger difference in electronegativity or smaller difference. Okay, it should be larger. Because, right, okay, we know from secondary school, ionic compounds are between metals and non-metals. Can you all see? Metals and non-metals are on opposite ends of the periodic table, right? Okay, so it's a larger difference in electronegativity. A larger EN difference. Okay, so in this case, because oxygen is more electronegative than sulfur, you should know that because oxygen is FON. That means Al and oxygen as a larger difference in electronegativity. Hey guys, you never know what they might ask you to explain. And don't just do the question and then just move on, because whatever is in your head, right, you may not be able to translate it into words very nicely. Okay, so this is how you translate it into words. Alright, should be okay lah, huh? Quite an okay question. Okay, but again, it's just boils down to the point of time management. Okay, but again, you guys never exceed the upper bound, so that's fine. All okay so far? Okay, we're gonna proceed to a rather challenging question now. Okay, a very, very application-driven question. Okay, so what I want you guys to do is this. Okay, go over to question 3. So you all don't have any questions for question 2? Okay, can go over to question 3. Okay, read through the question, right? I just need you all to try part 1 first. After you finish part 1, you can read part 2 lah, but part 2 is a bit hard. We'll try this ourselves together. We'll try this together. Okay, so just try B part 1 first. Okay, and okay, perhaps I just tell you one thing first, because you haven't learned organic chemistry yet. I tell you a few things. Ethanol is CH3 CH2OH. Okay, write it down first because it's the question in part 1, right? There are other stuff I'll tell you later. Okay, but this is just one thing you need to know first. Okay, and also, what do all these zigzag lines represent? Okay, these zigzag lines, I just need you all to know, it's just carbon and hydrogen atoms. That's all I'm going to tell you all for this. Okay. Remember what I said about carbon and hydrogen? That one will be useful for later on. Right? Part 1 must be able to get up, because we have learned this before, just in a very novel context. Okay, this. Right, okay, let's check our answer. For part one, it's all about drawing hydrogen bonds, okay? And just need to remember the hydrogen bonding criteria. Let's recap together. Can you tell me what's the hydrogen bonding criteria? Two things. Criteria one is what? FON, bond with H. Okay, we try to assign the criteria correctly. Criteria one is H bonded to F, O, or N. Either one of these are okay. The second molecule must have what then? Okay, lone pair of electrons on FON. Okay, good. Okay, so guys, this phospholipid molecule looks like that. Yes. Okay. Ethanol molecule looks like this. Can I ask you, this phospholipid, right, fulfills which criteria? 1, 2, or can be either one. Okay, 2. Can it fulfill criteria 1? Okay, so if you look very carefully, right, all these oxygens are bonded to 1. Okay, maybe because it's organic chemistry, to clarify this first. Okay, all these that you can see are all carbon atoms. Okay, so let me teach you again. Carbon, 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 carbon. And every carbon is bonded to an appropriate number of hydrogen atoms. So this carbon, right, has 3 hydrogen atoms actually, but they are not drawn here because hydrogen is actually invisible when we draw this kind of structure. Okay, we will learn this when we learn organic chemistry, but for the sake of this question, I just need you all to understand whatever that you can see, right, are all carbon atoms. But each carbon atom is bonded to hydrogen that you can't see. So, as you can see here, all the oxygens are bonded to carbon, right? So, there's no oxygen bonded to a H. So, in this case, it doesn't fulfill criteria 1. This guy fulfills criteria 2. So, let me just write here first. Phospholipid, criteria 2. If that's the case, that means ethanol must fulfill criteria 1. Does it fulfill criteria 1? Okay, based on the thing that I've given you guys, okay, it can. There's an OH bond, so this guy can definitely fulfill the first criteria. Okay, then of course, you'll be asking yourself, where can I draw the hydrogen bonds, right? Answer is, honestly, any possible oxygen is okay. Because as long as the oxygen has a lone pair, right, then it's okay. So in this case, you might see negative charges, it's okay as well. You want to put the lone pair here, fine. Okay, so I'll show you at least 2 answers. This guy has a lone pair, you need to show. And then it hydrogen bonds with the H bonded to the O to the CH3, CH2. Okay, all I need to do is to label hydrogen bonds. And at the same time, show me all your partial charges. Okay, here is partial plus, here should be partial minus, here should be partial plus, partial minus. So it comes in step like that. So that's one possible answer. Another possible answer I want to talk about, right, is if you chose the O minus. Can as well. Okay, O minus with the lone pair, that's fine. And then you bond it to the H, to the O, to the CH3, something like this. So these interactions are just your hydrogen bonds. But the last thing that's a little bit different are your partial charges. Okay, clearly, right, hydrogen has a plus, oxygen has a minus. But do you all need to put a partial negative charge here on oxygen? Okay, you can if you want to, but it's actually not necessary. You all know why? Yes, exactly. It already has a negative charge, so it already allows these interactions to form. The negative charge can attract a partial positive charge hydrogen. So there's actually no necessity to put the partial negative charge here. If you want to, it's fine, but I think it's best to just leave it like that. So that's how hydrogen bonds can also form over here, as long as you have a lone pair. Okay? So I'll draw 2 possible answers. You all just need to draw 1. All good so far. Okay, great. Okay, guys, what I want you to do now, right? I want you to think of the answer for part 2. You can try a bit, okay, but don't write too much because your answer might be wrong. Okay, later we'll write down the full answer together. But I need you to try to internalize the logic first of part 2. Okay, so it says something about soap particles. So if you relate your real life experiences, right? Okay, with the question over here, sometimes that real life experience can help you answer the question. Okay, this is about COVID, soaps, hand sanitizers. Okay, you guys should know roughly what direction they're trying to go towards. Okay, so now we are just incorporating intermolecular forces. Now I'm not going to time you guys here. I'm just going to give you guys a bit of time just to take a look first. Think of your answer. Okay, maybe you all underline some of the things in the question, right? And try to annotate a little bit of things. Don't just stare at it, of course. Okay, and I'll go over in a couple of minutes. Okay, we discuss this together. from an intermolecular force perspective, because here they use the word interactions. So that's how you identify the correct core concept. All right. So try to think of what interactions are formed in this entire hand washing process. Okay. Okay, maybe about 1 more minute, you'll just think through this first. Okay. You might have your own perception, but then later we will put that into the test. Okay. Okay, think of what happens when you wash your hands, then after that you, what happens when you put soap on your hands, then afterwards you wash your feet with water. Okay, so that's the whole sequence. All right, okay, come, let's discuss this together. All right, so I'm not going to give you guys the answers straight up. Okay, I want you guys to I want to hear what ideas you might have in this question. How you would think the mechanics of this works. Okay, so perhaps we start off first with identifying all the stakeholders, all the players in this question. Okay, so how many species are there in this question? 3. Good. Okay, so identify all the 3 first. Okay, number 1, when your hand has virus, your virus is your lipid. Number 2, you wash your hands with soap. Okay, so they will clearly interact with each other. But then finally, you need to use water to wash off the soap, right? So water will also help with breaking up the virus membrane. The key word in this question is breaking up the membrane. What's the membrane? The membrane is a lipid. So with whatever that we've learned so far, somehow this molecule, the interactions in this molecule must be broken and all that stuff. Okay, so perhaps with 3 different species, first of all, okay, they ask us to describe the interactions between soap and liquid, right? So let's just write down draw this diagram first. Okay, so we have soap having some sort of interactions with the virus lipid. Okay, first. All right, they ask you to describe the interaction, so you can score some marks here. Okay, so guys, what's the interaction between soap and lipid? Any suggestions? Soap is here, lipid is here. What kind of interactions can they form? Okay, PD, why? Okay, justify a bit. Between what exactly? Good. Okay, so you can clearly see this molecule is huge, right? Okay, but this part here is polar because of all the oxygens. This part also all polar because of the oxygens. Great. Okay, so we do know that there are PD interactions between soap and lipid. Why not hydrogen bonds, by the way? Yeah, okay, even this guy, we already established there's no H bonded to any of the O's. Is there any H bonded to any of the O's here? Also don't have. So cannot, unfortunately. Okay, so yeah, that's what we have. PD attractions. Okay, any other interactions here? Hydrogen bonds? Oh, okay, no. Okay, there's actually more interactions between soap and lipid. And let me point to you guys first. You all notice all these zigzag lines? It's huge, so we can't ignore it. Okay, right now you're only concentrated on one small part of the molecule. Not wrong, but it's not enough. Okay, look at this huge zigzag portions. What interactions do you all think can be formed between them? Are they good? How do you know that? Okay, carbon and hydrogens. Okay, I'm going to introduce the term for this now. Okay, since you all know it's carbon and hydrogens, okay, in organic chemistry, we call them alkyl groups. We will use this term when we explain the answer later. Okay, so anyways, all these alkyl groups are, what's the nature of the alkyl groups? Polar, non-polar? Non-polar. As I already told you guys, carbon and hydrogen, that's all you need to do. So you cannot ignore the fact that it's huge, huh? These things can interact as well. They're huge. So between the lipid virus and the soap, they can also form ID-ID attractors. Later in our answer, we specify. Now, when we draw a rough diagram, okay, we just list down possible interactions first. So as you can see, guys, it forms multiple interactions. So the soap can kind of cling onto the virus quite nicely, right? Okay, quite effectively. Imagine your soap cannot hold on to the virus. Is that a good soap? It's a horrible soap, right? You want the soap to get rid of the virus, so you have to make sure that interactions here are rather strong or weak? Strong. They have to be strong, if not break apart, then the virus still in your hand. It's horrible. Okay, so anyways, guys, after you wash already, right, you still need water. Okay? Water says here, right? They say soap and water. So guys, it's quite clear that water must interact with soap, right? Why is water able to wash off soap? Because their interactions have got to be strong or weak. Have to be strong, right? If not, you use water, the soap cannot disappear from your hand, right? Okay, so guys, what's the interaction between water and soap? Come on. How do you know that? Good, okay, water has the OH, right? And then here there's O's with lone pairs. So definitely between water and soap, you have a rather strong interaction, hydrogen bonds. Okay? So 3 players, all the interactions are already mentioned. So just by mentioning these, right, minimally you guys can get 1 out of 2 marks. Okay, the other 1 mark is a little bit harder to get because you need to tell me how it breaks up the virus membrane. So 3 parts to this question. You determine who is between soap and lipid. You determine what's between soap and water, and then finally link both of them together. How does it get rid? How does it destroy the virus? So this lipid must be destroyed. How? Can you all see how? Guys, I've listed out down all these interactions. What must we now explain? What's the differences between these interactions? Strength. Exactly, that's the only thing we learned, right? Hydrogen bonds are way stronger than PPD and IDI. Okay? So what does that mean? Imagine this, because when water comes in, right, from the tap, there's a force. It's like it washes away the soap, right? So you can imagine this way, you have to think of an eagle trying to, when eagles, they dive into the water to take the fish and then they immediately fly away, right? It's the same thing here. Okay, the water is like an eagle, right? Diving in for the soap and then just removing the soap with water. Does that make sense? And the act of this, like scooping down and removing the soap, what will happen to these interactors? They'll break. And the effect of breaking this will actually destroy or break up the virus membrane in that sense. Can you see that? It comes because the interactions here are stronger, it swoops in, takes the soap away by force. That's why breaking these existing interactors. That's why they cause lipid to break apart. Make sense? Okay, so how do you put it in words? Again, that one's a little bit of the harder part. Okay, but let's write down the answer. Okay, so mention all the interactions first. Okay, just answer the question. Okay, there are PD attractions. Okay, between the polar regions of soap and lipid. So this is how you can specify where are the PD attractions? The polar regions. Okay, but not only that, and ID attractions, okay, between the non-polar alkyl groups, okay, of soap and lipid as well. So here soap and lipid can form 2 different types of interactions. We specify non-polar alkyl groups. and polar regions. Then you tell me about soap and water, right? Okay, soap and water can form hydrogen bonds. And you can immediately dive to the idea of strength. We know hydrogen bonds are stronger. So, which are stronger, then the PD-PD and ID-ID attractions between soap and liquid. So this diagram really kind of helps us frame our answer. And then the last point to close off your answer, right, is kind of linking the micro intermolecular force concept to a more macro perspective, which is about actually what's going to happen, breaking up the virus membrane. It does. Water washes away and breaks apart the membrane. So this last part is kind of like a contextual thing. Okay, how does all the interactions point towards the idea of breaking apart? So you just link it back to the factor. Okay, so you mentioned the hydrogen bonds, and of course here we know we are comparing strength. Okay, then the idea here is about washing away and breaking apart. Not an easy question to score. It's really not easy. Okay, for 2 marks, yes, it might seem like a lot to write. Okay, but again, these 2 marks are hard to get. Okay, again, they don't want to give 3 marks, they could, but if they give 3 marks, more people will die for this question. Okay. So please try something like this where you are playing around with different ideas first. Okay, before you actually dive straight into the answer. If you go dive straight into the answer, right, usually you won't turn out well. Okay, so come up with something like this first. And okay, right, so good. Okay, so we have conquered all the harder questions here. Okay, I need you to now try part 3. Part 3 also rather interesting. Okay. This one, I think you guys can try your hand at writing the answer. So for 2 marks, I'll give you guys 3 minutes. Okay, so after 3 minutes, I will go over. Okay. First, I need you all to pay attention to the word how the interactions arise. So you need to tell me the origin of these interactions as well. Okay, how does it even come about? You can't just tell me the interaction and then just move on. Okay. Just about 30 seconds left. All good. Right, okay, time's up. Okay, so let's take a look at whatever the interactions are here. Okay, guys, what's the answer? You all just tell me what's the interaction first. Sorry, PD? No, it's not. Any other answers? Sorry? Ionic bonds? No, also. Okay, I'll answer every single one of your questions. Come on. Ideally, also not correct. Okay, so let's dispel everything first. Okay, we learned so many interactions. Okay, we solved the weakest one, IDID. Why is it not IDID? Okay, you see, dust is non-polar. Okay, sure, you probably think of IDID. But it's between dust and fiber. What's the important thing about fiber here? It is an ion, right? So we have to identify the species first. It's an ion because it's really positively charged. Okay, so between an ion and a non-polar molecule, ion definitely not ID attraction. You have to understand ID dash ID, right, means instantaneous dipole, induced dipole. Okay, that means in this case, there's already a charge, right? You don't have to create any dipoles or whatever. Okay, so not ID here. Okay, the next one you mentioned is, okay, generally mentioned PD, right? Okay, it's not PD as well because non-polar molecules do not have permanent dipoles. No such thing as permanent dipoles for non-polar molecule. Non-polar molecule only has instantaneous dipoles, which also causes induced dipoles to form. Okay, Ken? And then as you mentioned, ionic bonds. Okay, so ionic bonds is the closest we have so far. Okay, but ionic bonds are between ions. So, but the problem is that only one of them is an ion. The other guy is a non-polar, simple molecule. So cannot. Okay, if there are two ions, then sure, ionic bonds is definitely the answer. Okay, so what is a possible answer over here? There's one thing that we have learned, right, which is the closest to this question here. Ion dipole, right? Okay, because remember, ion dipole interactions is between what and what? Ion, obviously, dipole is referring to a polar molecule. But you notice, right, this is not the full answer because this is not a polar molecule, right? So have we actually learned ion and non-polar before? Not really. Right? We never really learned this interaction before. But I can tell you guys it's very close to ion dipole. Okay, so let's just answer this question first. Okay. Non-polar molecules, their electron cloud, how does it look like? Evenly distributed or unevenly distributed? Evenly, right? Okay, there's no electronegativity difference. So let me just draw a very nice circle. Okay, right now, guys, look at the evenly distributed electron cloud. Is there are there any charges here, partial charges or anything? Nothing, right? Okay, because it's evenly distributed, it is not polarized. But guys, if you put this non-polar electron cloud close to a positively charged region, what do you think will happen? Electrons are going to gravitate towards the positive charge side, right? So guys, what happens to the electron cloud of a non-polar molecule? It gets polarized, right? So how is it polarized? Okay, the electrons flock to the left or flock to the right? Left, because it's positively charged. So in this case, you see electrons gravitating towards the left side a lot, and then the right side less electrons. Can I ask you, on the left side now has a what charge? Is it just negative charge? Partial negative. Okay, take note, this is not actually an ion, it's partial negative. Right side is partial positive. Now guys, what kind of dipole is this? Is it a permanent dipole? It wasn't there in the first place, right? So guys, what kind of dipole is this? Okay, is also, or you could say induced dipole, because guys, induced means to create change in someone else, right? Here, this dipole was caused because it was caused by the ion. So this is an induced dipole. Now, okay, we shouldn't use the word instantaneous dipole, because instantaneous means it's created on the spot by itself. Was this created on the spot by itself? No. Instantaneous, like what I've explained during the lesson, at any point in time, the electrons are always moving, right? So at any point in time, it can randomly just become polarized like this. This is done by itself, no external factors, but this one was influenced by the ion. And because of that, right, this is induced, it's created by something else, it's affected by something else. Make sense? Okay, so guys, the answer in this question is actually this thing here, okay, plus and partial negative. Answer here is ion dash induced dipole interactance. Now I know you never really learned this before, and that's why exams can be freaking annoying sometimes, right? Okay, they can come out with this kind of nonsense. You never learned ion dash induced dipole, but guys, now that I've explained how it comes about, you have definitely seen the principle behind all this. Okay, so if the name just looks new only. So we just need to explain how this comes about, which is what we just talked about. Okay, so the fiber, okay, the fiber's positive charges will polarize the electron cloud of the non-polar dust particles. So notice how I am putting in context here, fiber and dust. Yeah. So now that it's polarized, right? Okay, it creates an induced dipole. It creates an induced dipole in dust. And that's pretty much all you need to say, thus creating ion dash induced dipole interactions. Your explanation is just to talk about how these induced dipoles come about, because ion don't need to explain, ion is just ion. Right, okay, Ken? So you can see how Chem bonding questions can really take a turn. Okay, it could be easy, but it could be as difficult as it like this. Okay, Ken? So you learn a new type of interaction, okay, must play by ear, essentially. Guys, we just finished up the last question. That was easy. Okay, so just give it a try. Okay, sometimes you notice the 2 marks in this question is definitely way harder to get than the 2 marks in the last question. Okay, so go and try part C, and then we'll be done for this part. Okay, perhaps the easiest question so far. Okay, let's go over the answer here. So it's not going to take too long, right, guys? They ask for structure and bonding, so clearly you know what kind of question type it is. So the structure of copper is what? Yes, okay, good. Dry metallic lattice. That's already 1 mark. Can you already see? It's so much easier to get a 1 mark here than the 1 mark in the previous question. Right? Okay, then afterwards, bonding. What's the bonding? How will you describe? Okay, metallic bonds, or you want to see electrostatic forces can also, but you honestly won't have time. Okay, metallic bonds between. Okay, if you say metal cations, they might penalize because they give you convex here. Copper. Okay, so they say copper, you must specify between the copper what cations? Copper usually exists as a 2+ charge, right? So you must mention copper 2+ cations. Please do not just give me a generic answer. The generic answer will never get you marks. Okay, copper 2+ ions and the C of what? Delocalize valence electrons. Now remember, the very first lesson I mentioned, you must tell me about the word valence. Very important. And that's it, that's 2 marks. But you see, sometimes the 2 marks, okay, you might lose it because you forget the word valence and whatnot, okay, which is a bit painful sometimes. Okay, but anyways, yeah, okay, this question, good question. Hot prelim question. Right? Yes, copper exists as Cu+, but in the actual metal itself, right, okay, you will see copper 2+ cations more. Copper plus is more of something that's created in an oxidation/reduction reaction. Yeah, here no, doesn't. It is not from. It's not in the actual structure, the lattice itself. Okay. Any issues? Okay, do I have? All right, we're gonna proceed over the other questions. We've just done the hardest question in this entire worksheet already. Okay, so let's see. I want you guys to try. Go over to question 6. I think question 6 is a good question. Okay, very good question. Okay, turn over to question 6. Okay, it's quite a long question, so we need to split it into a couple of parts. All right, for question 6, I just need you to try part A part 1 and A part 2 first. Okay, A part 1, A part 2. I'll give you guys a bit more time for this. Okay, 7 minutes. All right, 7 minutes for 2 parts. Okay, for the first part, before you explain anything, of course, you might more or less need to draw the structure of the compound first. Dot and cross or whatever. Then you can answer the question. Right? Here, after we finish these first 2 parts, we take a short break. Right? And we're going to draw the structure. Okay, you can treat OH, right, as a side atom. Okay, treat OH as a side atom. I know OH is two atoms now, okay, but then you can just put OH, 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 and then B in the center. Yeah. Okay, so you want to split up the O and the H also can. So I give you guys a bit of tips here. Okay, you see dot across is endless possibilities. Okay, so many possibilities you can stuff like this. Okay, so perhaps right, okay, what you can do is put boron in the center, which makes sense. Okay, and then afterwards we have OH on each side. OH, OH, OH. So you see three side atoms, but you leave a bit more space because you still need to draw the bonds between the O and the H, which I'm sure you can guess what bonds they are. Right? H, O, OH, and then OH. So essentially what's happening here is that boron is surrounded by three oxygens. Then each oxygen is bonded to an H further out. So it kind of branches out like this. Okay, so just doing all the bonds. Okay, I suggest you start from the outside, the very outside first. So you start off with the outermost atoms, which is hydrogen, and then you link inwards. Okay? Because hydrogen is the easiest to draw, everyone knows that. Don't need me to go through the shape of this compound, then you can answer the question. Okay, so come on, we look at the shape first. Okay, so you will notice again, more stuff that you've never seen before. Okay, where your side atoms have multiple atoms. Right, then you keep branching out like this. Okay, so this is how you arrange first. The reason why I asked you to start at the outside, because H can form how many bonds? One. Instantly, right? You can already fill up one bond each, like that. And then, right, guys, you must ask yourself, oxygen tends to form how many bonds? Two. So it already forms one bond on the left. It means this guy must have how many bonds? One. So it's like 1, 1, 1, 1, 1, 1, right? You just fill it in also. This 1, 1. Just make sure the dot and cross is alternated correctly. Then for oxygen, just going to fill out all the valence electrons. So we have 4 more valence not used in bonding. Okay, then you finally go towards the center. Okay, boron, is there anything else we need to fill up? Lone pair? No, that's not correct. Actually, this is the answer already. Boron has how many valence? 3. 3 valence, 3 crosses, finish. Okay, I know sometimes it's tempting to put something here, right? Okay, no. Okay, that's your answer. Can see that? As for this question, they're asking for the shape. And once again, guys, shapes are always with respect to the which atom? Central atom, which in this case, they clarified nicely for you guys, boron. Okay, so boron's shape, you must refer to BS-EPR theory. So you might want to look back at your notes and see what BS-EPR theory says. Okay, don't copy out BS-EPR theory because that one you're just copying. They're asking you to refer to the BS-EPR theory. Okay, so just like capture the main idea of BS-EPR in this question when you want to express the shape. Okay. So I don't expect you guys to memorize the word for word the definition now, but you refer. But when you refer already, you tell me what there, right, captures the idea of forming shapes, right? After you try to finish the first part, let me just go over the explanation first before you all move on to the second part. Right, just make sure our answers are polished enough, right? Then I'll show you guys how to write an answer. Okay, let me just look through the answer for part one, right? So if you read the question carefully, right, it says with reference to VSEPR theory. What does this mean? Okay, do not just copy straight up from the VSEPR theory. Okay, if they ask like this, okay, define the VSEPR theory and then explain the shape and bond angle. Okay, if they ask you to define, right, then yes, you're going to copy up everything. Okay, but now they just ask you to refer. Okay, so what does VSEPR theory talk about? Okay, like you don't need to tell me the exact definition, but what's the main essence behind it? What's the overall idea? Electrons want to be as far apart from each other on the central atom as possible. Okay, because that's the way to do what? They are doing all this to minimize mutual repulsions and hence the compound is the most stable. Okay, that one, the word stable isn't in the definition, but you must know. All right, okay, so in this question, right, we know that we have all the shapes and all that. I'm pretty sure you all can tell me what the shape is. Okay, but how do you refer to the VSEPR theory? Okay, first, you must tell me how many bond pairs and lone pairs, right? Okay, that's how you determine the shapes. So just go straight to telling me how many bond pairs are there. Okay, good. How many lone pairs? 0. Okay, so there are 3 bond pairs. Okay, and must mention lone pairs are 0 lone pairs. Okay, around boron in BOH3. Okay, so what? How will it, with 3 bond pairs, right, the furthest they can go apart from each other is 120 degrees, right? Okay, but why are they doing so? Okay, so you can tell me to minimize repulsions and to maximize stability. And see that? Less repulsions, more stability. That's what all molecules are trying to aim towards. And in order to do so, once again, electrons are intelligent species. They know what to do okay, in order to achieve this goal. Okay? The bond pairs will arrange themselves as far apart as possible around boron. So don't use the word central atom. Use the actual central atom here, which is boron. So notice, right, I'm just taking the first definition of VSEPR and making very subtle references, like minimize repulsions, arrange themselves as far apart as possible. Okay? So it's not about copying and pasting, it's about just subtly seamlessly transitioning into that. And then you can conclude. That's why, right? Okay. Boron has a trigonal planar shape, 120 degrees. 2 marks. Now all the shape and bond angles, right? Fundamentally, you must look at the number of bond pairs and lone pairs. So I just mentioned that first. Okay, that's always the first thing you talk about. Then you look at into the concept. Having 3 bond pairs, what's the best way to make themselves as far apart as possible? Trigonal planar. Okay. So I didn't talk about the second definition of VSEPR, and that is totally fine. Okay, we don't need to talk about the second definition because that one, right, is to compare the different strengths of the repulsions. Okay, having a lone pair means you will have stronger repulsions, right? But is there a lone pair in this question? No. So there's no need for you to include the second answer here. Right? Even if there was, right, there isn't much. You're not comparing repulsions in this case. You're only talking about one guy. You're not comparing his bond angle with someone else. Right? Okay, so there's even if there's a lone pair, right, there's no need for you to mention that in this question. Okay, good. Okay, so good question, part 1. Right, anyways, guys, okay, I think you guys can try part 2. It's quite okay. Because, guys, let me just tell you all first, preface this first. BOH4 minus, actually, you can build off your answer from where? The first one, right, guys? BOH3, BOH4 minus, there's only a subtle difference, right? Okay, so you're going to try. Okay. Use the current structure that you have drawn, right, to save time for the next part. So it's like you spend more time on the first part, but it's offset by the second part, right? Remember the minus charge, huh? What does the minus charge mean, right? Bracket the whole thing with the minus charge. Okay, any ions, don't forget the overall bracket. Okay, good. You guys have mostly gotten the answer. Okay, they did ask you guys to clearly indicate any dative bonds, so just go and indicate that as well. Okay, now let's go over the answer here. Okay, but let's have an expansion exercise to this question, because here they only ask you to draw dot and cross, but to test you all on your shapes and all that, I'll ask you as well. Okay, Cl can only form one bond, so it's just a single bond, and single bond. Okay, boron only has 3 valence, so make sure there's no lone pair in this case. Perhaps, right, I think it's good to translate this into the structure with the shape and bond angle. Guys, what shape is this? It actually is the same as just now, right? Okay, trigonoplanar shape. So perhaps since there's a lot of space, I'm just going to draw this. I mean, it's for your own practice anyway. Okay, we're going to write down the name as well. I think the more you all write down, right? It's a psychological thing. Okay, the more you write down, the more you remember. Oh, might as well, right? Yeah, okay. Hello? So 120 degrees. Okay, so how do you draw BOH4 minus? I hope you all know this, right? From BOH3 to OH4 minus, there's only an additional what? OH minus, right? Yeah, okay, that's what I was referring to. Yes, there's an additional electron. Okay, but there's an additional hole like OH minus, right? So we need to fit this inside somewhere. Then obviously we can fit it down here. Okay, the electron, yes. Negative charge means you must add an electron to who? Which is, okay, good. I like how you use the word most electronegative, which is oxygen. We have 3 atoms here. So oxygen here is how many electrons? Oh, after you add already, 7, right? Okay, 7 can form how many bonds? 7 can only form one bond, right? Then what's going on over here? Okay, so you notice something, OH minus, right? Okay, the H can just form a single bond first, right? Actually, this single bond. And then the dative bond comes here because you have 7 valence. Just give one dative bond straight to the boron here. Okay, wait up. This is the correct answer. Okay, but do remember to put your negative sign with the bracket. Now, some of you may be asking this question. Okay, let me change this. Okay, you all got answer first? Cannot. Just now, one of you guys mentioned, what if, right, the dative bond goes to hydrogen first, right? So dative bond to hydrogen, and then here is what? A normal single bond, right? Now, is that possible? Okay, it looks possible, right? Oxygen here is 1, 2, 3, 4, 5, 6, 7 electrons because after getting the negative. Does that make sense? Okay, it looks correct, right? Okay, but the reason why this is wrong is because you have to understand it's actually OH minus existing as a species first. And then OH minus comes in to donate it to boron here. After all, guys, you all notice boron currently has how many valence in total? In total is 6, right? And 6 means it has a what? Okay. Boron has 6 valence electrons after bonding, meaning to say it has a vacant what? Orbital. Great. Okay, so it has a vacant orbital. Okay, so it can accept electrons. Okay, it can accept electron pairs from other species. That's why the dative bond should be here to boron, not to hydrogen. It just doesn't make sense. And just now it's wrong. Also because, guys, boron doesn't have 4 valence, right? Okay, so just pay close attention to that. Okay, boron doesn't have 4 valence. You can't share anymore. Okay, so the dative bond must be here and here. Alright? Can So yeah, they ask you to label the dative bond. I don't know why they ask you to do this, honestly. It's such a waste of time. Okay, but it's just dative bonds. Okay, no? Then just get the 3 marks. 1 mark here and then 2 marks here. Okay. Okay, so good. Okay, know how to draw some of these structures. Okay, we're gonna take a short break first. Later we finish up the rest of this pattern. Maybe you can try another one also. Alright. Okay, actually this question, the rest of this question a bit long. So I'm gonna take a break first until 5:45, 7 minutes. Okay. Okay, so let's continue for the last part of the lesson, right? I'm gonna finish up the rest of this question. There's a bit of more concept stuff as well. Okay, so I want you to focus on part 3. Okay, part 3, this one they only gave 2 marks, but I honestly feel this deserves 3 marks because you need to write a lot. So don't be afraid to write more than the lines allocated because I feel that I tell you first there's more to write. Okay, so for this one, right, just A part 3 alone, I will give you guys 6 minutes. Okay, so I give 1 mark 2 minutes. Okay. Remember, they said with reference to structure and bonding, so you must answer the question. What's the structure and what's the bonding in each molecule? Okay, we have 2 minutes left. Okay, we have 1 final minute. Try to wrap up the answer by then. And time's up. Right, okay, let's take a look at the answer. Okay, rather lengthy answer. Let me just write down the format first. Okay, you guys should roughly have the same format to keep your answer short and concise. Okay, so these are the blanks that we need to fill in. Right, let's take a look. Okay, so a rather lengthy answer. Again, right, I really think that this is worthy of a 3-mark question. Okay, but to go back to the principles first, okay, let's ask ourselves structure and bonding. Okay, so this concept here. Okay, what's the structure and bonding of BCl3? Simple molecular, BOH3. From your structures that you drawn earlier is also simple molecular, right? So these two are in the same class, we can explain them together. But then this guy is what? Okay, it is a giant ionic lattice, so this is a little bit of a special structure that can talk about it itself. That's how you can see my answers split into 2 paragraphs. The first paragraph is between BCl3 and BOH3. They both have simple molecular structures. Okay, and then over here, right, your next paragraph is on the giant ionic lattice for NaBOH4. Okay, before we look into the factors, why is BOH3 having a much higher melting point than BCl3? So do you all remember the principles behind comparing the melting points of simple molecules? Simple molecules, what is the thing that affects its physical properties? Atomic radius? No. Okay, what affects the physical properties of simple molecules? Okay, all that is basically your intermolecular forces, right? Okay, so we need to compare the factors affecting the strength of the intermolecular forces. But what's the first thing that we need to discuss? Okay, as far as mentioned, we always need to compare electron pile size first. And then what next? If the cloud size cannot be compared, then we can look at the type of intermolecular forces. So follow this order and let's see which one we need to use in this question. Okay, so guys, you look at BCl3 and BOH3. I need you to always look at the size first. Guys, what's the size in this case? Who is bigger? Okay, you do not need to calculate the MR. You can kind of estimate yourself. Okay, who is definitely bigger? Okay, it's actually BCl3. BCl3 is bigger. Okay, why? Okay, you see B and B, right? Then there's 3 of them. Chlorine, one chlorine is 35.5. One OH is 16 plus 1, 17. So can you see who's bigger already? Okay, so definitely BCl3 is bigger. Having a larger electron cloud means what? Larger electron cloud is more easily polarized, right? So BCl3 should have stronger or weaker ID. Larger means stronger actually. Okay, larger electron cloud should have stronger ID attractions, meaning it needs more energy to overcome, right? But does this fit the data that it is given you? No. So we cannot use electron cloud size in this question, not because the sizes are similar. Okay, not because the sizes are similar, okay, but because it doesn't explain the question. So we are only left with the other choice, which is the type. BCl3, what's the intermolecular force here? To determine what's the type of intermolecular force, you need to check whether it is polar or non-polar, right? BCl3, polar or non-polar? Just now you all drew the structure of BCl3, right? It looks like this. So is it polar or non-polar? Can you all see the dipoles are cancelling each other out in all directions? So BCl3 is a non-polar molecule. It should be just ID attractions. Can? So that's what I'm going to mention in my answer. BCl3 has ID attractions. You don't need to tell me whether it's polar or non-polar. If not, your answer is too long. Okay. How about BOH3? Now, some of you guys may think BOH3 is also non-polar, but that's not the case. BOH3 is a bit more special. Okay, I know just now it was a trigonal planar shape, right? So I know oxygen is more electronegative than boron. So you would think that same as BCl3 cancels out in all directions. But actually that's not the case. Because O is bonded to H, right? And that O bonded to H is actually in a band structure. So it's in a band shape. So let me show you guys, right, that actually there's an overall dipole movement. B and O, yes, the dipoles are pointing this way, but O and H, the dipoles are pointing this way. Can you see that? Now, overall, where is the dipole pointing towards? Okay, overall, it is pointing this way. Can you see that? Here, same thing, pointing towards O, pointing towards O. The dipole overall is pointing downwards. Same thing here, pointing to O, overall is pointing downwards. Can you see here? Two arrows are pointing downwards and one arrow is kind of pointing to the side. Does this side arrow cancel out the bottom arrows? No. These arrows don't cancel each other out. So because of that, there's an overall dipole moment. BOH3 is polar. What is the interaction of BOH of a polar molecule like BOH? What's the interaction here? Is it PDPD? It's actually hydrogen bonds, right? Because if we can draw two of these boronic acid molecules, right, you can see there's O bonded to H. O bonded to H and there's O lone pair. So this polar molecule is held together by hydrogen bonds. So you see, I'm not in this question, especially for structures like this. You see that? Okay, it's because O has two lone pairs and two bond pairs. I'm not drawing the lone pairs in this case. That's why it's actually bad. Like you refer back to your structure of BOH3, oxygen can be a central atom by itself also. So it also has a shape. Two lone pairs, two bond pairs, it will be bent. Okay, so it's bent across all three structures. So that's actually the shape of BOH3. Can? Can, Alright, then finally, right, okay, we need to fill in everything. BCl3 is IDID, BOH3 is hydrogen bonds. So guys, does this explain this question? It doesn't explain the question, it does, right? Okay, hydrogen bonds are stronger. So you see how I just continue my sentence. I don't repeat the thing again. BOH3 is hydrogen bonds which are stronger and requires more energy to overcome. So it flows very nicely and you've cut down your answer into just this short paragraph. Okay, first? Okay? Yeah, so comparing your factors is not very easy sometimes. Okay, sometimes you really need to look at it carefully. You identify the wrong interaction, right? They're just gonna minus marks. Furthermore, these 2 marks, and they can only minus 1 mark. They don't minus partial marks in GC really. So very strict. That's why it's hard to score. Okay? Because I say it's a very good question, you might want to start this question. Okay. Okay, then afterwards we can talk about any BOH4 very, very simply. Okay, so you all can copy in a bit. Let me just explain the last part. BOH4 is giant ionic lattice, right? Held together by what kind of bonds? Ionic bonds, right? And we do know that ionic bonds, bonds in general, are stronger than intermolecular forces. That's why it has the highest melting point out of them all. This one I think should be quite easy. Just make sure you have the keywords. Okay, it is held together by, okay, even says strong ionic bonds between the cation and the anion. Please specify the cation and contextualize your answer. Okay, then you just compare. The ionic bonds are definitely stronger. Okay, bonds definitely stronger than intermolecular forces. So it is stronger than the. Oops, it's BOH4 minus. Okay, so BOH3. Okay, so you can say the ionic bonds are stronger than the hydrogen bonds in BOH3. Okay, which require once again more energy to overcome. Okay, if you can also phrase it a bit differently. Here I say the ionic bonds are stronger than the hydrogen bonds. But if you say that the ionic bonds are stronger than the hydrogen bonds and the IDID can also, but then your answer must be which requires the most energy to overcome. Depending on how you phrase your answer, you use the word more or use the word most, it's up to you. Because here we got 3 structures. Okay, again, it all depends on how you phrase. So that's the answer to this question. Okay, so the answering part, not the issue, is about how you arrive at the answer. And if you're wondering how this works, right, okay, it's kind of like how vectors work. You all know how vectors works. Okay, so it's like the arrow is tail to head, then you join the tail to head, then afterwards the arrow is pointing this way. You will see that the overall dipole moments, right, are not pointing anywhere in particular, that's cancelling each other out. Okay? Not easy question, so I suggest try to see if you can redo the first couple of parts yourself again. Redoing questions is another one of my principles when it comes to studying. Okay, redoing questions is sometimes better than doing more questions. Okay, because you revisit them to see whether you really understand the corrections. Okay, so far? Okay, so I'm gonna tell you guys again, there's homework. Okay, I know there's homework for the chem bonding tutorial as well, but again, you'll just take your time for this. Okay, the chem bonding tutorial comes first, afterwards is this worksheet here. Okay, again, chem bonding is that important. I really want to make sure your chem bonding is good. Okay, that's why we got so many practices. Okay, so let me show you guys what questions we have for homework. So for homework, right, again, just do question 4, a rather short question. Question 5, a rather easy explanation question. Question 6, just finish up whatever we haven't done yet. Finish up. Okay. Okay, again, same thing. When finish ready, just send answers to me. Okay, send your answers, right? Okay, afterwards, okay, question 7, not that important because we tried before already. Finally, question 8. Yeah, okay, then that's pretty much the core of the worksheet. Question 7, I don't think is very important. Okay, so yeah, take your time to do this. Again, we are doing so much practice for chem bonding because it's that important. Your chem bonding gone, right? Then your answers all lose marks. Okay, good. So that's it for today, right? Then next week we're gonna start on a new topic, pH state. Yeah, that was a bit more technical, there's not much content. Right? Okay, so yeah, that's it.